In the last two videos, we have talked about the work done. Now in this video, let's talk about energy. We define the energy, it is the capacity of doing work or the ability to do work. That means we are defining energy in terms of work. Energy can be again divided into two categories. One is the kinetic energy, the other one is the potential energy. In this video, we will concentrate on kinetic energy. The word kinetic has come from kinema, the meaning motion. So here, kinetic energy can be defined as the energy possessed by a body when it is in motion, or otherwise the work done by the object when it is in motion. To quantify the kinetic energy, we can define that it is the work done by the object when it is in motion. Because we can find out what is work done. And with the help of that work done formula, we will try to derive a formula for kinetic energy also. Now, we know that the work done is equal to F times displacement. Now I can replace this F by ma from Newton's second law. We know from the equations of motion v square minus u square is equal to 2as. Now we can replace this as from this equation as v square minus u square by 2. Here v is the final velocity and u is the initial velocity. If you consider the initial velocity is 0, then this as can be replaced by half v square. Now let us substitute that here. Then we get half mv square. So this is the work done. W is equal to half mv square, and this is only known as the kinetic energy. So we began with the formula of the work done and we have derived a formula for kinetic energy. Let's derive the kinetic energy formula with the help of calculus. So here first we begin with dW, the small amount of work done in moving small displacement ds. Therefore dW can be written as F times ds. I can replace this F by ma as the force is equal to ma from Newton's second law. Now I'll write this a as rate of change of velocity from the definition of acceleration, and then I'll write ds. By rearranging these terms, m times dv, and it is ds by dt. We know that ds by dt is nothing but the velocity. Therefore, this is mv dv. Now, if I wanted to know the entire work done, so I can integrate mv dv from 0 to velocity v. We know the integration of v as v square by 2 because we know integral over x to the power of n dx is nothing but x to the power of n plus 1 by n plus 1. By using the same formula, here it is v to the power of 1, therefore v to the power of 1 plus 1. So Now I can write this W as m v square by 2, which is to be operated in the lower limit 0 because we considered the object initially is at rest, and then upper limit v. So when we replace these limits, mv square by 2, and in place of v we have to substitute 0 in the second case. Therefore finally the formula has come out to be half mv square. This kinetic energy is a function of speed. V square is nothing but v dot v. So it is a scalar product. So kinetic energy K is directly proportional to v square. So what does it tell us? Suppose if you increase the speed, then the kinetic energy is also increased. But how? Suppose if you double the speed, then the kinetic energy will be 4 times the old kinetic energy. Why? Because in place of this v, we have to replace 2v. Suppose if the speed is raised by 10 times, that is, in place of v, we have to replace 10v. Now, if you square it, it becomes 100v square. So, if you raise the speed by n times, the kinetic energy will be raised by n square times. But with reference to mass, if you say, if the mass is doubled, how can you change the mass of an object? You cannot. Mass is doubled in the sense, we have taken initially 1 kg substance, suppose, then we have to take 2 kg mass. That's the meaning of mass is doubled. So when we take the object whose mass is twice than the first mass, then in that case, the kinetic energy of the body increases by 2 times only. It is linear function, provided the speed of the object should be same. Energy is a scalar quantity, therefore kinetic energy is also a scalar quantity, and the units of energy, that is joule, as it is defined in terms of work, the units of energy and units of work done remain same. Therefore, the kinetic energy can also be expressed in terms of joule, or in CGS system it is in terms of erg.